Okay, so now let's focus on the three approaches. I briefly go over them. The first approach is using hollow glass fibers. The examples are like this. These are hollow glass fibers. The darkness you see is the emptiness inside the fiber. So they can be incorporated into carbon fibers, into a carbon fiber composite. Basically, you lay them parallel to the carbon fiber composite. In this approach, the glass fibers are one directional in one way. Typically, you avoid using, making them two-dimensional or three-dimensional using this approach one. 2 and 3D often comes with these two approaches. So both of them, these 2 and 3, can be 2 or 3-dimensional. The reason you don't go with one glass fibers, hollow glass fibers, to make this holes in multi-directional holes is because, for instance, if I wanted to put a glass fiber in this direction, not just one in this direction, but also in this direction, now the carbon fibers had to go over them. So if I, for instance, chose to look at this guy from this direction, what I would have seen is a glass fiber. This is a hollow glass fiber, and a carbon fiber, which pretty much appears like a line, would have gone like this. These are extremely wavy fibers, and this will significantly reduce the strength of carbon fiber composite in that direction, because these fibers can easily buckle in compression. So because of that, typically we avoid having 2 or 3-dimensional things with hollow glass fibers, networks with hollow glass fibers. Instead, we focus on these two that I will explain in the next slide. So the first one, direct ink writing of a fugitive network. The idea is that I print a 3D network like this. Initially, there's no matrix. It's a hollow structure. Think of it as the frame of a building before any floor is laid down. What do you see? It's that. The only difference is that the network can be somehow removed, either melted away or heated up to a temperature that will be decomposed and moved away. Now, then after this fugitive network is made, it's put inside a mold, and all around it is filled with a matrix. So, for instance, imagine you put a mesh of wires inside a glass of water, and then you freeze the glass of water. When you take it out, those meshes are inside that glass. Here, instead of glass, it's the chemical reaction of curing of the matrix that turns it into a solid, and these guys will be embedded in the matrix. Then you heat it up or somehow decompose with some form of treatment. You decompose this guy, and in place of that, the holes will be left. Easily, you can generate 3D structures out of this guy. So that's one approach. The other approach, so in this case, this network was printed. In another approach, this network can be woven from a fiber that is degradable. For instance, what you see in this graph is a PLA fiber that polylactide fibers, PLA. So where's the, okay, so it's PLA. That a little bit of a catalyst. Now, the chemistry of the catalyst is not important, some form of silicon oxide, that when you heat it up, so at 240 degrees, black is without catalyst, red is with catalyst. It decomposes and goes away. This is just a fiber. This is the sacrificial fiber, okay, not the load-bearing fiber. Now you can weave a 3D network or a 2D network or a 1D network of these PLA fibers. And again, just like the previous slide, pour around it whatever matrix you have. And then you cure it, and then you get rid of, for instance, by heating it, you get rid of the sacrificial material. You need to make sure your sacrificial material decomposes at much lower temperatures than the matrix decomposes, because you don't want to damage the matrix while you're decomposing it. This is a very interesting approach. They could even make junctions between the pores. This is an example where after 60 minutes, this is a PLA fiber. This is PLA fiber decomposing, and this is the black parts is actually the hollow core. And this is basically black parts means PLA is removed. And then here, so as we go from here to here, as we go from here to here, the PLA is decomposed. Now, this approach can very well be incorporated into composites. Basically, you can use, for instance, you can use the load-bearing fibers as a platform to weave these sacrificial fibers around them. For instance, here, these are glass fibers. The orange ones are glass fibers. We've used them as a platform to weave around them this sacrificial fiber, which eventually turns into microchannels. So it could also be carbon fibers. And then we fill everything with the epoxy, and then we get rid of the fibers, the sacrificial fibers. Holes are much larger than carbon fiber diameter for reasons that I explained. So, and in this case, they did an experiment that the two types of healing agents are fed in from two sides. And there is this, the double cantilever beam fracture test. They showed some healing efficiency. Basically, they opened the crack. They measured the toughness of the virgin material. Close it, pump the healing agents in, let it cure, redo the experiment. They saw some measures of healing in this structure. Now, I call this sacrificial part 3 or scaffold part 3, because if you have these holes in the fiber, there are many other things you can do, many other cool things you can do with it. For instance, one example that I really, really like, this is the case for heat shields. Basically, imagine, for instance, a vehicle re-entering into the atmosphere of Earth. Temperature goes up at the at the tip of the spaceship. So you want to reduce the temperature. One way to do it is to carry the heat away. How can you do it? Well, you can imagine you have a structure like this. And so what you do is you pass a cool or coolant through it, just like a radiator in our cars, same concept. And so now this is wavy so that you can take heat in and away from the structure. So if I cut it at multiple levels, at every cut, I see a different amount. I cut these tubes at a certain point. So they measured the temperature as a function of distance at different planes with respect to the surface that is heated. And they demonstrated that indeed you can see some sort of cooling. I'm sorry, this is not as a function of depth, although as a function of depth is also explained in the paper. This is as a function of time. And so as they go to more and more times, indeed, the cooling takes place in this material. So I am going to stop here and continue in the next video.